In the last presentation, I hopefully gave you a little bit of an intuition of what a derivative is. It's really just a way to find the slope at a given point along a curve. Now we'll actually apply it to some functions. So let's say I had the function f of x is equal to x squared. And I want to know, what is the slope of this curve? What is this? My pen, I need to get another tool. What is the slope at, what is the slope at x is equal to, let's say, at x equals 3? What is the slope of x? So let's draw out what I'm asking. So that's a coordinate axis. That's the x coordinate. And that's the y coordinate. And then if I were to draw, let me pick a different color. If this is, so we want to say, what is the slope when x is equal to 3? So x is equal to, say this is x of 3, this is x equals 3, not x of 3. And of course, when x equals 3, f of x is equal to 9. We know that, right? So what we do is we take a point, maybe a little bit further along the curve. Let's say this point right here is 3 plus h, right? And I keep it abstract as h because, as you know, we're going to take the limit as h approaches 0. And that this point right here is what? It's 3 plus h squared, right? Because we're just, the function is f of x is equal to x squared. So this point right here is 3 plus h, comma, 3 plus h squared, right? Because we just take 3 plus h and put it into x squared, and we get 3 plus h squared. And this point here is, of course, 3 comma 9. What we want to do is we want to find the slope between these 2 points. I really have to find a better tool. This one keeps freezing. I think it's too CPU intensive. But anyway, so we want to find the slope between these 2 points. So what's the slope? So it's the change in y. So it's 3 plus h squared. I'm going to try it. 3 plus h squared minus this y, minus 9, over the change in x. Well, that's 3 plus h. That's 3 plus h, right? 3 plus h minus 3. Minus 3. So if we simplify this top part, or if we multiply it out, what's 3 plus h squared? That's 9 plus 6h, right? Plus h squared, and then you get the minus 9, and all of that is over, well, this 3 and this minus 3 cancel out, so all you're left is with the h, right? And even if we simplify this 9 minus 9, they cancel out, right? 9 minus 9. So let me go up here. So what we're left is we're left with 6, this pen keeps freezing, it's 6h plus h squared over h. And now we can simplify this, right? Because we can divide the top and the bottom, the numerator and the denominator, by h, and you get 6 plus h squared. So that's the slope between these 2 points, right? Is 6 plus h squared. So if we want to find the instantaneous slope at the point x equals 3, f of x is equal to 9, or the point 3, 9, we just have to find the limit as h approaches 0 here. So we'll just take the limit as h approaches 0. Well, this is an easy limit problem, right? What's the limit of 6 plus h squared as h approaches 0? Well, it equals 6. So we now know that the slope of this curve at the point x equals 3 is 6. The slope here is 6. So if you actually did a traditional rise over run, this slope, this change in y over change in x is 6. So we have the instantaneous slope at exactly the point x is equal to 3. So that's useful. We were able to find the exact, if this was the graph of someone's someone's position, we would then know kind of the instantaneous velocity, right? Which is, well, I won't go into that. I'll do a separate module on physics. But this was useful. But let's see if we can do a more generalized version where we don't have to know ahead of time what point we want to find the slope at. If we can get a generalized formula for the slope at any point along the graph, f of x is equal to x squared. So let me clear this. So we're going to stick with my pen. F of x is equal to x squared. And we know that the slope at any point of this is just going to be the limit, the limit as h approaches 0 of f of x plus h minus f of x, all of that, over h. And all this is, this part right here, this is just the slope formula that you learned years ago. It's just change in y over change in x. And all we're doing is we're seeing what happens as the change in x gets smaller and smaller and smaller as it actually approaches 0. And that's why we can get the instantaneous change at that point in the curve. So let's apply this definition of a derivative to this function. So, and actually, if you want to know the notation, I think this is the notation Lagrange came up with. This is equal to f prime of x. Don't take my word on it on Lagrange. You might want to look it up on Wikipedia. But this means the derivative of f of x is f prime of x. So let's apply it to x squared. So we're going to say the limit as h approaches 0 of f of x plus h. Well, f of x plus h is just x. This pen driving me crazy. X plus h squared, right? I just took the x plus h and put it into f of x minus f of x. Well, that's just x squared over h. And this is equal to the limit as h approaches 0. Let's just multiply this out of x squared plus, what is this, 2xh plus h squared, right, plus h squared, minus x squared, running out of space, all of that over h. Let's simplify this. This x squared cancels out with this minus x squared, right? And then we can divide the numerator and the denominator by h, and we're left with the limit as h approaches 0 of, let's see, numerator and denominator by h of 2x plus h. Well, this is easy. This is just equal, if this goes to 0, this is just equal to 2x. So there we have it. The limit as h approaches 0 is equal to 2x. So now we know that, and this is equal to f prime of x. So the derivative of f of x, which is denoted by f prime of x, is equal to 2x. Well, what does this tell us? What have we done for ourselves? Well, now I can give you any point along the curve. Let's say we want to know the slope at the point 16, right? When at the point 16, comma 256, right? That's a point along f of x equals x squared, right? It's just 16 and then 16 squared. What's the slope at that point? Well, we now know the slope is 2 times 16. The slope at that point, if my pen works properly, the slope is equal to 32. Whatever the x value is, you just put it into this f prime of x function, or the derivative function, and you'll get the slope at that point. I think that's pretty neat, and I'll show you how, in future presentations, how we can apply this to physics and optimization problems and a whole other set of things. And I'm also going to show you how to find the derivatives for a whole set of other functions. I'll see you in the next presentation.